It takes a powerful engine to propel a ship like a cruise liner or a cargo vessel. Turbochargers help make it possible. They can double the diesel engine's power, taking it to 100,000 horsepower or more. They also do it more efficiently by using exhaust gases to run the compressor. In a ship's engine, the turbocharger is a welcome source of fresh air. It compresses up to 60 meters of air per second and thrusts it into the engine's combustion chamber to boost performance significantly. Production starts with the turbine wheel that extracts the exhaust gases. A long cutting tool, known as a broach, carves a fir tree profile along the edge of a steel disc. This profile is designed to intermesh with the geometry of the blades. Next, a computer-guided saw slices a brass alloy cylinder into smaller pieces to produce bearings to support the turbine shaft. They make numerous bearings in a range of sizes and materials for different turbochargers. Computerized tools drill holes and mill the surface of an axial bearing that will fix the turbine rotor in the casing. This is the completed bearing. An engineer inserts one of the turbocharger's nickel alloy blades in a mold, with the foot of the blade protruding. He slides the mold directly under a spout, which dispenses a hot liquefied tin alloy. It fills the mold to the brim. The tin alloy solidifies and encases the blade just below the foot. This creates a structure that will fit into a clamping device in the grinding operation. Next, the tin-encased blades are inserted into tensioning devices in the grinding machine, with the feet protruding. Inside the tensioning device, a clamping mechanism grips the blades. As coolant flows, a computerized grinder carves a specific geometry into the feed, one that's designed to engage with the fir tree profile on the turbine disc. The machine releases its grip so that the blades can be removed. They break off the tin alloy structure, liberating the blade inside. It's now ready to be assembled to the turbine wheel. The blade foot is slid into place in the turbine disc. One clip is bent back halfway with pliers. The alignment is then tightened with a clamp. The clip is hammered down even further until it's flush to the blade foot and the turbine wheel. This secures the blade to the wheel. This process continues until the blades are fixed to the entire circumference of the turbine wheel. It takes 41 blades to complete the job. Next, computerized tools mill the aluminium compressor wheel as the table it sits on angles it for cutting. The tools form blades and carve grooves between them that make the compressor more aerodynamic. The more aerodynamic the compressor is, the more air the ship engine will receive for combustion. Here's the compressor wheel before and after the milling operation. The compressor is then lowered into a chamber and spun a lot faster than it would normally operate. This is a safety test. It confirms that this compressor can withstand a speed of 27,000 revolutions per minute without braking. The compressor wheel then goes for an ultrasonic cleaning. High-frequency sound waves ripple through the water to scrub off any grease or contaminants. When it's finished in the ultrasonic bath, a blower is aimed at the compressor wheel to dry it. It's then placed into another dryer to remove the residual moisture. The unit is then left to fully dry undisturbed until it's ready for the next stage. After the drying process is complete, a technician shines an ultraviolet light onto the surface of the compressor wheel. This illuminates any fine cracks that could compromise its quality. But with no cracks found, the rotor assembly now begins. Bearings are slid onto the main shaft and turbine. With a crane doing the heavy lifting, the center hole is aligned with the compressor wheel and the shaft. As it's guided into place, it fits snugly to the bearing. A cone-shaped cap is screwed onto the end. With the turbine wheel at one end of the shaft and the compressor at the other, the core parts of this ship's turbocharger have been assembled. The rotor can now be locked in a balancing machine. The machine gives the rotor a high-speed spin. Sensors detect the speed, the angular position of the rotor, and any possible imbalances. The team uses this information to calculate how much material must be removed from the rotor to bring it into balance. Then the final assembly of the turbocharger begins. The team screws the bearing casing to the gas outlet. They assemble 3 bearings to it. This insert, called the labyrinth cover, will act as a seal for the turbine disc and shaft. The long bolts fit into holes in the bearing casing. Moving around to the other side, the protruding bolts are secured with nuts. With the compressor wheel removed temporarily, the shaft is slid through the center bearing, which pushes the turbine wheel snug to the labyrinth cover. On the other side, a part known as a labyrinth disc is bolted to the casing. The labyrinth disc seals it from the hot turbine exhaust gas and prevents oil leakage. Then the compressor wheel is reinstalled on the protruding shaft. Meanwhile, rock wool insulation is wrapped around the gas inlet casing, which is made of cast iron. Exhaust gases as hot as 500 degrees Celsius will flow through this part. After encasing the part with a heat-resistant fabric jacket, it's ready to be mounted to the gas outlet casing. It's moved into position with a crane. The holes in the part are aligned with the threads in the casing so that it can be bolted into place. They then install the cast iron casing around the compressor wheel. Like the casing on the other side, it's secured with numerous nuts and bolts. They now hoist an insert part into place between the compressor wheel and the casing. Air will be sucked into the space between the insert and the compressor before flowing to the ship engine for combustion. This turbocharger is now ready to be installed in a ship's engine in the factory's assembly hall. Once in place, the engine is fired up and its performance evaluated by a computer. They test how much the turbocharger increases the engine's power and assess its impact on fuel efficiency. The turbocharger meets expectations. In operation, it performs in much the same way as a smaller turbocharger found in a car or a truck, but delivers far greater air pressure and therefore far greater performance. So the captain should be able to rely on it when the seas get rough and the going gets tough.